Okay. Okay, we were studying the norm of bounded linear operators. Maybe less than this. Okay. I remember that we defined or determined the d of x and y, and then we this example we had this theorem. If x be finite dimensional and y be non-linear space and t from x to y be linear transformation, so t is continuous. So every linear transformation from a finite dimensional vector space to a normal space is continuous. And this is an example. Let P be the linear subspace of C0 and 1. Means all continuous, all polynomial functions like t from p to c defined by t of p equals P prima 1. P prima means the derivative of P. This is also a continuous transformation or bounded transformation. Lemma. If x and y be non-linear space, and t from x to y be continuous, then the kernel of t is closed. You see, kernel of t here means the set of all define again the kernel of t. This is the set of all x from x in x such that the t of x equals 0, t of x equals 0. So we can write kernel of t as the t minus 1 of the singleton 0. We call a set with one element a singleton. So as you see, because kernel of t is the t minus 1 of singleton 0, and singleton 0 is a closed set in Y, so the kernel of t is closed because the inverse of any closed subset by a continuous function will be closed. Definition: if x and y are normal space and t from x to y be a linear transformation, the graph of t is linear subspace of GT. Linear subspace denoted by g of t as a subset of x cross y. So the graph of a transformation t or a function t is the set of x and tx for all x in x. As you see, for example, if fx equals x power 2, the graph of this is this shape or figure. This is the set of all x and x power 2 for all x in R, and this is a subset of R power 2. Let me see. Okay. Lemma. If x and y are known spaces and t be a continuous linear transformation, in this case, g of t, the graph of t is closed. So the graph of t of linear continuous transformation are closed. This is the proof of the lemma. For proving that G of t is closed, we should show that for any sequence xn, when xn approaches to x, we should conclude that the t of xn approaches to t of x. Lemma. Let x and y be non-linear spaces and S and T be bounded linear transformation from x to y, or belong to P of x and y, such that the norm of S of x is less than or equal K1 dot norm of x, and the norm of T of x is less than K2 of norm of x for all x, and let lambda be a scalar or a member of F. Then we have A, the norm of S plus T of x is less than K1 plus K2 dot norm of x for all x, and the norm of lambda Sx is less than the absolute value of lambda K1 norm of x for all x. And C, P of x and y is a linear subspace of L of x and y, and so P of x and y is a vector space. Because of A and B, as you see, A and B says that the linear combination of two bounded linear transformation will be a bounded linear transformation. So the set of B of x and y is a linear vector space and is a linear subspace of L of x and y. So this is a vector space. We have some exercises in this section. I will send you the solution of the selected exercises. Now for this section, we have the norm of a bounded linear operator. As we see that the B of x and y is a vector space, this is a vector space. So if we associate a norm to this vector space, it will be a norm space. Norm space. So we want to show that B of x and y is also a norm space. For defining a norm on this space, we need this lemma. Before that, we say that the supremum of the normal T of x for all x less than or equal 1 equals the inf of k such that the norm of T of x is less than or equal k of norm of x for all x. We have this equation So and also this inequality, the normal T of y is less than the supremum dot the normal y. So if we call the norm of k, norm of t as the supremum, it will be a norm. This fact is in the next lemma. Let x and y be normed spaces. If this function from b of x and y to r is defined as the norm of t equals the supremum of the set of all norm of t of x for all x less than or for all x such that the norm of x is less than or equal 1, this function will be a norm on b of x. The proof is a little difficult, so I left it for your study only. Now we will have this definition. Let x and y be normed linear subspaces, linear spaces, and t belongs to b of x and y. The norm of t is defined by the norm of t equals the supremum of the set norm of t of x for all x such that the norm of x is less than or equal 1. So from the previous lemma, we saw that this definition will be a definition of a norm. Now we define the norm of t as this supremum. Another definition for f as R or C, let f of p, f power p, be the whole p triples by number of in f. So for a matrix of dimension n cross n, if T is a linear transformation from Fn to Fn such that the T of x equals Ax. In this case, T is a bounded linear transformation, and we define the norm on matrix X as the norm of T. So for a matrix A, we can define a norm by the normal operator T. And this is an example for T from CF of 0 and 1 is all continuous function from 0 and 1 to F T by this Definition: T of f equals f of 0 is a bounded linear operator, and the norm of t equals 1. Here is the proof of the example or the solution. Theorem: let X be a non-linear space and W be a dense subspace of X. Then we say that W as a subset of X is dense when the closure of W equals X. Now let Y be a Banach space and S belongs to B of W and Y. We have the following properties. A. If X is a member of X and Xn and Yn be sequences in W such that the limit of Xn equals the limit of Yn equals X, then S of Xn and S of Yn are both converge, and the limit of Sn equals the limit of Sy. It means that if S be a bounded linear transformation and two sequences approaches to one point, then the sequences S of Xn and S of Yn converges to one point in Y, or the limit of the sequence S of Xn is the same as the limit of S of Yn. B. There exists linear transformation T from X to Y such that the norm of T equals the norm of S and T of X is equal the S of X for all W, for all X in W. Here T is the extension of S, or S is the is T with the domain W. The proof is a little difficult, so I left it for your study, only for your study, but they won't be in the midterm or final exam. Definition: let X and Y be nonlinear spaces and T belongs to the L of X and Y. If the norm of T of X equals the norm of X for all X, we say that T is an isometry. So when we say that a function is an isometry, it means that the norm of T of X is equal to the norm of X. The internet is weak now and we should wait Okay, we can continue now. Oh no. Okay. I hope we can continue. Okay. Example, if X is a norm space and I is the identity linear transformation of X, then I is an isometry. I means the identity function, and identity function is a function with this definition. For all x we have I of x equals x. So the norm of I of x equals the norm of x, and so I is an isometry, and the norm of I equals 1. The norm of I equals 1. Another example, if x is a sequence in L power 2 and y is such a sequence, when we shift or transfer x1 to the second place and x2 to the third place, and so on, y will be in L2, L power 2. B, the linear transformation S from L2 to L2 defined by this definition is an isometry. We call this linear transformation the operator shift. Notation. This is unilateral shift, or simply this is a shift. This operation is called unilateral, or simply a shift. Lemma: let x and y be nonlinear spaces, and let T be in L of x and y. If T is an isometry, then T is bounded and the norm of T equals 1. I said before that this lemma that any isometry has the norm 1, and so this is bounded and continuous. Definition: if x and y are nonlinear spaces and T is an isometry from x to onto y, then T is called isometric isomorphism. Here T is invertible because this is isometry and this is onto or surjective. This is injective and surjective, so this is isometric. And this linear transformation, which is isometry and onto, is called isometric isomorphism. And x and y are called isometrically isomorphic. If there is an isometric isomorphism from x to y, these vector spaces or norm vector spaces are called isometrically isomorphic. Theorem: let H be an infinite dimensional Hilbert space. So H is a Hilbert space that is such that the dimension of H is infinite over the field F with an orthonormal basis En. Then there is an isometry T of H onto LF L power 2F, means all sequences in L2 with elements in F, such that T of En equals En I group for all n. En I group is such a sequence that the nth place of this sequence is 1 and the other elements are 0. This is the proof of the theorem. I left it for your study. Crawler. Any infinite dimensional separable Hilbert space H over F is isometrically isomorphic to L of 2 power L power 2 of this is the direct result, direct corollary from the previous theorem. Before H is separable, then there must be an orthonormal basis En for H by theorem 3.52. So H is isometrically isomorphic to L power 2F by the previous theorem. Again, some exercises. I will send you the solution of selected exercises. Now we are going to study the space V of x and y. Theorem. This is an important theorem. I write it important. I wrote it important because this is an important theorem. If X is a non-linear space and Y is a Banach space, then V of X and Y is a Banach space. You know that if X and Y are normed spaces, V of X and Y will be a non-linear space. But to be in Banach space, it is enough that Y be Banach space. Definition. Let X be a normal space, linear transformation from X to F. F is the scalar field this this set of linear transformations from X to F is called linear functionals. So when we say that we say linear functional, it means a member of B of X and F. In some books, B of X and F is denoted by X star or X prime. So X star or X prime means the bounded linear transformation from X to F. This space is called the dual space of X, and is denoted by X prime. As you see in this book, the dual space of is sometimes denoted by X star. In this book, the dual of X is denoted by X prime, but is some other books like functional analysis by Walter Rudin. In that book, the dual space is denoted by X star, not X prime. But here is denoted by X prime. Crowley. If X is a norm vector space, then X prime is a Banach space. Because X star or X prime is the B of X and F. And because F is R or C, and both R and C are complete, so P of X and F must be complete or Banach. And we have the Crowley, this Crowley. If X is a normal space, the dual space or X prime is always Banach space. Lemma. If X, Y, and Z are non-linear spaces, and T belongs to B of X and Y, and S belongs to B of Y and Z, then the combination of S and T, SOT, will be in B of X and Z. And we have this inequality. The norm of SOT is less than the norm of S dot norm of T. Definition: let X and Y and Z be non-linear spaces, and T belongs to B of X and Y, and S belongs to B of Y and Z. Their composition SOT of S and T will be denoted by ST. So instead of denoted this composition by SOT, we denoted this by ST, and we called it the product, like the product of two numbers. We called this combination or composition the product of S and T. Okay. Unfortunately, the internet is okay. Maybe we can. Notation B of x and x when x and y are the same or equal. We denote B of x and x as the set of all bounded linear operators from x to x by B of x. So instead of B of x and x, we denote this vector space as V of x. You see, if x and y are the same, instead of B of x and y or B of x and x, we write B of x. Now we have this lemma, but before this lemma, we should say that an algebra, when we say that this is an algebra, it means that this set has two operators, the additional operators and the dot operators. Now, because P of x, we can define two operators, the addition of two operators like S and T, and the combination of two operators as the product of two operators. So we have, for example, S plus T and ST and TS. So the B of x is an algebra. We have this lemma: let x be a non-linear space. B of x is an algebra with identity, and hence this is a ring with identity. An algebra is also a ring. A ring means a set R with two operations, plus and dot. But algebra is a special ring, not all ring. Algebra is also a ring, but not all ring. This is a ring such that the B of x and plus is a vector space. So when R with plus be a vector space, this ring will be called an algebra. This algebra can have identity or not. If this ring has a number 1, such that A.1 equals 1.A and equals A, we say that this is a ring with unit. Now, this lemma says that P of x is an algebra with identity, or a ring with unit or identity. And B, if Tn and Sn are sequences in B of x such that the limit of Tn equals T and the limit of Sn equals S, then the limit of the composition of Sn and Tn equals St. Here the limit is in norm. Okay, I think that's enough for now. Here. The number of page 107. Please remember this page for the next session. And I remind again that the next session we will start at 3:30 o'clock. The class will be at 3 o'clock and half. not 4 o'clock. A half an hour sooner than before classes. Please remember that the time of class is half an hour sooner because of the azan in Iran. Okay? So the class is ended, and if you have any question, I will be at your service. Any question? No question? So remember the time of the class for next session. Okay, so goodbye.